Today we will discuss magnetic materials. Basically here we discuss four types of magnetic materials. First one, diamagnetic materials. These diamagnetic materials has no permanent magnetic moments. The existence of small non-zero magnetic moment in this material is attributed to the orbital motion of the electron. If we calculated diamagnetic susceptibility by the Langevin classical theory, we see the magnetic susceptibility will be negative. So chi will be negative. Now if we calculated magnetic susceptibility by Langevin theory, it will be chi equals to minus nz mu 0 square average value bar square by 6 me, where n equal to number of atom per unit volume, z equals to number of proton, and average of r square will be the average square distance of electron from the nucleus. Me, the mass of the electron. So we see that diamagnetic susceptibility independent of temperature, and also diamagnetic susceptibility proportional to the number of atoms per unit volume, and also average square distance of electron from the nucleus. Now we draw some important curve. First one, magnetization versus magnetic field. Which will look like this one. Next, we draw susceptibility versus temperature, which will look like this. Next, we draw 1 by chi versus temperature curve for this diamagnetic material, which will look like this. Next, number 2, we will discuss paramagnetic materials. Basically, paramagnetic materials has permanent magnetic moments. In the absence of the external magnetic field, there is no net magnetization. But when we apply an external magnetic field, there will be a net magnetization. Similarly, if we calculate paramagnetic susceptibility using Langevin classical theory, which form Curie law written as chi para equals to C in mu 0 mu square by 3 kbt equals to C by T, where mu will be magnetic moment and C will be the Curie constant. So we see that chi para is inversely proportional to temperature. Now we will discuss some important curve. First, magnetization versus magnetic field curve, which is look like this. Here in this curve, we find a saturation magnetization, which is MS, where M is equal to N mu. This will be the value of saturated magnetization. Next, we draw chi Ferrara versus temperature curve, which is look like this. Sorry. Okay. Next, we will draw 1 by chi versus temperature curve, which is look like this. Sorry, here will be 1 by chi and the slope will be 1 by c. As chi equal to c by t. So 1 by chi equal to t by c. So next we will discuss ferromagnetic material. Ferromagnetic material show the spontaneous magnetization. It means ferromagnetic material show magnetization in the absence of external magnetic field also, unlike ferromagnetic material. Ferromagnetic susceptibility will be calculated by the Curie-Weiss law, which show chi ferro equal to c by t minus tc, where tc will be Curie temperature and c Curie constant. Below the Curie temperature, the material will behave as ferromagnetic, and the temperature above the Curie temperature, the material behave like paramagnetic. Now we draw the graphs image, which is looks like a hysteresis loop, like this. This is look like this. Next, we draw susceptibility with temperature, and this curve look like this. Chi temperature T, below Tc the graph look like this. The above Tc the graph look like this. Now we draw the curve 1 by chi with temperature. 1 by chi with temperature. This will be look like this. The slope will be 1 by c, and this equation will be minus tc by c, and this transition happened at Tc. Next, antiferromagnetic material. Antiferromagnetic material. In the absence of external magnetic antiferromagnetic material also show the zero magnetization. Only when the external magnetic field apply, they show the non-zero magnetization. The ferromagnetic susceptibility equal to 2C by T plus Tn, where Tn is Nil's temperature. Nil's temperature. When the material below the Nil's temperature, it behaves like antiferromagnetic. But when the material placed above the Nil temperature, it behaves like paramagnetic. We draw the curve susceptibility versus temperature. Susceptibility temperature for the antiferromagnetic material. The graph look like this. PC, this one's 2C by Tn. This region antiferromagnetic, this region paramagnetic. Next we draw 1 by chi versus temperature. 1 by chi versus temperature. This graph look like this. This one Tn slope 1 by 2C. This point Tn by 2C. So summary will be we write chi versus temperature curve for all 4 types of materials. Then we get this was antiferromagnetic, this was para, this was ferro, and dia will be this one. So it will be dia. And next, if we draw 1 by chi versus temperature for all 4 types of material, then the curve look like this one. for para. This will be for para. This will be ferro. This will be for antiferro. And this will be for dia. Dia, antiferro, para, ferro. This one TC, this one TN. Thank you for watching. That is that.